Chapter 4 is the last chapter that we will be working on this semester. So once you've made it to this point, take a big breath and recognize that we're almost there and you're almost finished. Chapter 4 is about scatter diagrams, or as I'll call them, scatter plots, because I kind of think that's the standard name, and linear correlation. And then section 4.2 is going to be about linear regression. And we'll just kind of combine those together in one set of videos here today. Okay, so first, what are we doing on section 4.1? Well, section 4.1, we're taking a set of data, which looks like this, and we're trying to visualize this on a graph. And the way we visualize it is we think of this as being an x and a y. And so we think of one of them as being x and one of them as being y. And in fact, the one that we think of as x is always what we call the explanatory variable, and the one that we think of as y is what we think of as the response variable. It turns out there are a lot of problems that we do that it's not really clear which one is explaining and which one is responding. In this problem, however, we have an individual who begins a weight loss program, and he's weighing himself periodically over a month to see how his weight does. And so in this case, we would expect that it is the days in the weight loss program that's telling you what the weight is. We wouldn't expect that somehow his weight is causing him to be in the weight loss program. We think that the days in the weight loss program are causing the weight. So we kind of think of that as being the explanatory and the response variable. Additionally, we mentioned this earlier in the semester, but it's always good to keep in mind that there could be other variables going on. So there could be a lurking variable. And lurking variable is a variable that's not collected. So why is this person losing weight? Well, it could be that the diet is working and that's helping them lose weight. It could be they started a new exercise routine, and maybe the exercise routine is the one that's causing the weight loss and not the diet. Maybe the diet's actually not that great of a diet, but something else in their life is making them lose weight. It could be that they got a tapeworm and the tapeworm is causing them to lose weight. Oh, okay, that was kind of an unpleasant thought. Okay, sorry about that. At any rate, we think of these explanatory response and lurking are variables that's not collected. Well, the first thing we want to do with this data once we have it is we want to put it on a scatter plot or scatter diagram. And the simplest thing to do with a scatter plot is just to get yourself a graph, and here's my graph. And I went ahead and set it on up with my numbers on here. 255, 250, 245, and here's my little zigzag to show that I made a break in my graph. And I'm just going to plot each point. So I'll put 0 and 252, which looks right around there. Then I'll put 5 and 249, so that looks like that dot should be right around there. 7 and 250. 12 and 247, somewhere around here. 19 and 246. And then 28 and 244. So we can kind of see the values, and what you can see is that the values are slowly decreasing, and so we would expect this to have some sort of relationship. And what we're trying to do in this section is capture how closely they're related to each other. The first way that we're going to capture this is with what we call the correlation coefficient. And so the first way we're going to try to capture this is with a correlation coefficient, and correlation coefficient is what we call R. Okay, so the correlation coefficient is what we call R. And what the correlation coefficient is measuring, we're not going to completely derive this formula, but let me just tell you a little bit about how you would derive it. What you do is you would take the average of all these x values, which I did this beforehand, and it happens to be 11.22, so it happens to be somewhere right around here, or at 11.83. And then you take the average of all the y values, which happens to be somewhere like this, somewhere like 48, and then you put a dot right where that is. And then what we measure is what's the relationship between those to the right and up and down. So you actually multiply this. So if I think of this point here has an x distance and a y distance. And what we notice is that x here has increased by about 5 and has decreased by and is decreased by about 2. So you see each pot has an increase and decrease, and then we kind of combine those together. So what we're trying to do is measure what are the differences and what's the combinations. And what you'll notice is that in this case, every time you increase x, y decreases. And that gives me a negative correlation coefficient. So this correlation coefficient is negative if when one variable increases, the other decreases. Increases means the other decreases. So sorry, there's just my kind of lazy notation there, but hopefully it makes a little bit of sense. So that's what it means to have a negative correlation coefficient. And notice that's what's going to happen. So if we move, anytime you move to the right in x, y goes down. Versus if we had a set of dots going in the other direction, then we would come up here and have a point like this, and we would get positive and positive. And so a positive correlation coefficient means that when one variable increases, the other also increases. So they either increase together or decrease together. Okay, so that's the big idea of a correlation coefficient. I would kind of normally spend a little bit more time talking about the formula and where it comes from. And here's our formula, but I kind of made a decision that because this formula is clunky, it's actually not even a perfect formula itself. This one is kind of a simplified version of the right formula, and it gives you just an approximation of the correct answer. So what I'm going to do is, instead of using this formula at all, what I'm going to do is just delete it, and we are not going to use this formula to calculate things. Instead, we'll just use our calculator, and our calculator can calculate it for us. Okay, so feel free to delete that formula. Just know that it's not magic, and what your calculator is doing is not magic. It's just measuring how much up and down and these differences here, and trying to get some idea of the product of these when you multiply these together. Okay. So one thing that's important is that a correlation coefficient always runs on a scale. And when we have a correlation coefficient, you always get a number, and the number is always the lowest it can get is -1, and the highest, let's put the line right here, and the highest it can get is a +1 with 0 right in the middle. And so we already know that negative means they go down, and positive means they go up. But what does the scale mean? Well, -1 means it's a perfectly downward scale. It makes a perfect line. Right? A +1 would be a perfect line with a positive slope, and 0 would be a jumbled mess that has no slope attached to it. And so if we're somewhere in the middle, like this picture, if I look at this, what would I expect? Well, I'd expect my correlation to be negative, and R is the letter that we always use for correlation coefficient. So I'd expect R to be negative, because it's going down. I wouldn't expect it to be -1, but it looks like it's going to be fairly close to -1. Notice how this kind of goes down. It almost has a little bit of a line shape to it. So if it made a perfect line, then it would be -1. It's not jumbled enough to be very close to 0. So negative, close to -1. So that's kind of what I'm thinking as I go through this graph. We'll learn how to do this in our calculator very, very shortly. Okay. When we turn over to section 4.2, which is the next place that we want to go, what we want to do is we want to create a linear regression. So 4.2 is linear regression. And all we really mean when we say linear regression is that we come to this picture and we try to draw the best line possible going through all of these dots. And so what is the best line possible going to look like? I don't know, maybe something like that. So you take all the dots that you could possibly come up with and make the best possible one that you can. What do we mean by best possible? Well, what we actually mean is if we took the dot on this line and the dot here, we could measure how off they are, how far off they are. And every single line that you could possibly draw has some combinations of how far off they are. So what we would do to come up with the best one possible is we would try to make those errors or those distances, how far they're off, as small as possible. We would actually square them all and then square root it and find the least squared error. But what we're trying to do is make these values right here as small as possible. So take every line possible and find that one. By the way, if you've had calculus, this is a maximum minimum problem. So this is one where you could set this up as a calculus problem and then take a derivative and set it equal to 0. We, of course, won't be doing that. But once we have this line, the line is always written with an equation, and I'm going to apologize right now for the equation. This is the equation that the book uses. It uses y hat equals a plus bx. The y hat is just to distinguish the difference between y, which is your value. So think of it as y being the value here in the x value, being the height of that dot, and y hat being the dot on your line. So this is just distinguished. These aren't the actual values from your sample. These are the values that come from your equation. So we just use the y hat to distinguish the two. Okay, but y hat, and then they use this equation a plus bx. And again, I'm going to sincerely apologize for this notation. I don't like it, but this is what the book uses, and I feel like I'm kind of stuck with it. What you'll note, the reason why I don't like it is that usually when we think of a line, we think of it as mx plus b, where this is the slope. But notice that means this one here is telling us the slope. And then b, which usually tells us the y-intercept, in our equation is telling us slope, b is now telling us the y-intercept. So as you look through this problem, what you should think is the letters are a little backward to what we're used to. But it's pretty simple. Whichever number is attached to the x is your slope. Whichever number isn't is your y-intercept. So if I were to look at this line, I could just kind of make an approximation of the line. And it looks like my y-intercept is, we were at 250, maybe somewhere around 251. And then my slope, let's look at what happens on my slope. So I'm going to start at 251. Let's just make a really big triangle out of this whole thing. Okay, so this triangle, and then just do a rise over run for this triangle. What is my rise over run? Looks like my rise, looks like I went down, let's see, I went from 51 to maybe 44. And so that puts me at -7. And then my run was somewhere around 28, so maybe -7 over 28. So I might guess that a good approximation would be 251 minus 0.25x. So this is my guess. This is not going to be the actual answer. We'll calculate that in a moment. Okay, how would I find the real answer? The way I would find the real answer would be to use these formulas. You might know what's coming. I'm going to put x's through these because we're not going to use these formulas either. We're going to use our calculator. Our calculator is going to be able to compute all of this for us. Okay. All right, so we're going to make our calculator do these things and compute them for us. So now let's go ahead and jump forward and do that, and then we'll come back to this problem. By the way, I know some of you have different versions of calculators, and it's possible that your calculator is struggling to do this computation. If so, I might suggest you use Excel. And Excel works extremely well at this. If not, you can actually talk to me and I'll give you a bunch of other choices. Okay, so the first thing we need to do when we get this is we need to come in, we need to put our numbers in stat. So I'm going to go to the stat button. You can see it right there. And then I'm going to go to edit and I'm going to type all of my numbers in. So 0, 5, 7, 12, 19, and 28, and they're all typed in. So hopefully I typed them in correctly. Now I'm going to quit. And the next thing I'm going to do is I'm going to hit Stat, Calc, and then do linear regression. There's linear regression ax plus b, and most of you, here's a linear regression a plus bx. They're actually the exact same thing. The only difference is which order the calculator gives you your numbers. So if you pick ax plus b, it'll give you the slope as a and the y-intercept as b. If you pick this option, it'll give you the slope is, or the y-intercept is a and the slope is b. So it'll do the exact same thing. It just tells you, it'll do the exact same thing. It just tells you slightly, just the order in which it tells you your answers are slightly different. I'm going to choose this first one because it's the easiest one to get to. So I'll choose it and I'll hit enter. And what you can see is it gave us our linear regression line. So that's our line. Now you may be asking, where's the y-intercept? Well, some of you will already have the y-intercept printed right here. If that's the case, congratulations, you're done. You can write, I mean, not the y-intercept. You might ask, what's the correlation coefficient, r? Some of you already have r right here. If that's the case, congratulations, you're done. If that's not the case, let's do a little bit of work. So we're going to make our calculator tell us r. So the way I'm going to do that is I'm going to go to the catalog button. Catalog is a button you don't use very often, but what it does is it has every single command your calculator could do. So second, catalog, and what you'll see is here's a list. Every single command programmed into your calculator is somewhere in this catalog. And I'm going to keep scrolling down until I get to the one called diagnostic. Diagnostic is nice because it allows those R's to show up. So you hit diagnostic on, click it, and hit enter, and it'll say done. Okay, great. Now we'll go back to stat, back to calc, back to linear regression, and hit enter. And you'll notice now I have the same values, but I've added R and R squared. So I have all my values here in my calculator. Hopefully it makes a little bit of sense. And there you go. I also have instructions in the notes if you want to figure out how to make your graphs pop up. It's not super hard to do it. To make your graphs pop up, you go to y equals, and then you have to turn on your plot, and hopefully that makes your graph show up. And then I always do zoom, and there's a zoom stat button, and that zooms it right on that zooms your dots just perfectly. And so see, it scaled everything so that it fits the exact scale I wanted, and there's the dots. And you see that looks pretty close to what we had earlier, doesn't it? They're all pretty similar. Okay, if I wanted to add my equation after I've already ran the regression equation, I have to go to variables, which we've used a little bit. We've used the distribution button, and then go to y variables. Let's see, is it variables? Yeah, statistics. And then equation and regression equation. And what that'll do is that types that equation in for you. You could type it by hand. You could just write in those numbers and type it by hand. And then hit graph, and what you see is there's that line going right down the middle. So you've got that line that goes right in the middle of the dots. That's that line that's the closest we could possibly come to hitting every dot. We don't hit them all, but that's as close as we can ever come. And you see, we didn't do a bad job of approximating all this earlier, did we? Okay, so now that we've got these things done, let's come and let's actually write out what our answers were. So what did I get for my responses? My correlation coefficient R was 0.965, negative 0.965, and notice that kind of matches. We said it would be negative and close to -1, so that's negative. It's actually even more negative than I might have guessed. And then our equation is y hat, and then we look and we got a negative 0.2735. I guess I don't need that many decimals. X, so notice that's the number with the X on it, plus 251.24. Okay, that's enough decimals. Okay, so here's our problem, and we've got kind of all these things. We've got kind of it all laid out here. So here's our equation, and here's that. So now what I'm able to do is I'm able to come tackle these questions in exercise 4.3. So let's grab this over here, and let's move this out of the way. And let's ask some questions about that. Let's ask some of the questions that you might have if you were this person on the diet. So the first question would be to find the linear regression. And so part A is already done. So part A is that equation right here. Okay. Part B, what weight would you expect the person to weigh 14 days later? Well, if you're trying to make an estimate 14 days into the graph, the best estimate you can do, so we're at 14, we don't know where the black dot really is, but we know that this green dot, if it's on the line, should be pretty close. So we will use the value on the line to estimate where the black dot should be. And that means we just plug 14 into that equation. So I'm just going to go negative 2735 times 14 plus 251.24. And so I'll just plug it in. Negative, oh, that should have a decimal in front. 0.2735 times 14 plus 251.24, and I got 247.411. So that gives me a pretty good estimate. So we don't know the actual weight on day 14, but we know that this is pretty close to the right answer. Part C, how much weight would you expect them to lose per day? Notice the amount of weight you're losing per day is just this slope number. So this is the weight loss per day. Per day is equal to the slope. So what does that mean? That means we're expecting to lose about, so the answer here is about 0.27 pounds per day. So that's pretty good. If you're on a diet, I think if you're on a diet and you could lose like a quarter of a pound a day, I think you'd be pretty happy with that diet. By the way, what does this number tell us? The 251.24 tells us your weight on day 0. So that's the weight when you started your problem. Okay, finally, part D asks us, what would we expect our weight to be 100 days in? And so we do the same as B, except we put 100 into our equation and see what we get. Oh. And so I'm going to come here and type in 100. So do all that times 100, and I got 23.89 pounds. Now here's an interesting question, and the question that we need to go is, well, do we think this is reasonable? Or importantly, which answer do we think is better? Answer B or answer D? Which one do we feel like is the more accurate answer for the two of the two? And I hope that you're able to understand that answer B is the more accurate answer, because when we look at our graph, we kind of know what the weights are doing for the first month. We have no idea what happens 100 days later. One thing I can be pretty confident is that this trend won't happen forever. Because, for example, what would happen if we were to say do 1,000 days later? If you did 1,000 days later, then all of a sudden your weight is negative 22.26 pounds. So like somehow you've died and your body has turned into gases that weigh less than it, you know, that weigh less than air. Okay. Well, we know that that's not possible. So we know that this trend can't happen forever. At some point, the trend starts to bend, and the answer is we don't know when. Well, this brings up a really good observation, and this is what in statistics we call the difference between interpolation and extrapolation. So interpolation, you can see the word inter in here, and that kind of means we're inside of something. So interpolation are estimates within the collected data. And what you'll find is that estimates within the 0 to 28 range tend to be pretty good estimates because we actually know the weight during that period. So we can be pretty sure that during that 0 to 28 day period, we can make pretty good guesses as to what his weight would be. So that's interpolation, weights that happen inside that period at some point. Extrapolation, however, are estimates made outside the collected data. Oh, I really messed up spelling up here. And so that's like this example where we looked at 100. So notice the 100 is so far off the chart that there's no telling if the trend keeps going. As a general rule in statistics, interpolation is often considered pretty safe if you use interpolation to make estimates. You can be pretty confident in those estimates. Extrapolation can be very risky because in order for extrapolation to be useful, you have to know that whatever the trend is will continue. And the fact of knowing that a trend will continue or won't continue is not a mathematics problem. This is a human problem. This is a problem of us looking at the forces affecting the forces affecting your environment and saying whether those forces will continue to act in the same way or not. So extrapolation, particularly the further you get from your range of data, the more off that extrapolation becomes. Okay, so again, extrapolation isn't always bad, but to use extrapolation, you have to know the pattern continues. And by the way, whenever, whenever we're using extrapolation, or whenever you're reading the news or looking at some other information, extrapolation is usually where they'll make a mistake. So this is where they will draw some sort of conclusions that are not the right conclusions. Okay, so finally we have the coefficient of determination. And the coefficient of determination is r squared. And it is simply whatever that number we got for r was earlier squared. And so if you looked at your data, actually when you do the calculation, it shows up when you turn your diagnostics on. And r squared for us was 0.931. The nice thing about r squared is it turns all your negative numbers positive. So it gives a way of comparing all of your numbers to each other. And furthermore, so r is always between 0 and 1, and the closer it is to 1, the better, the stronger your correlation is. But the coefficient of determination also has another meaning, and it kind of tells you this number can be kind of thought of as a percentage. And so what you can think of is that this is like a 93%, and that means that as we look at our data, well, we know our values are decreasing. We know that the weight is decreasing, and what it says is that about 93% of the decrease is correlated with the days on the diet. So that means there's about a 93%. It does about a 93% complete job of describing why the weight is going down. However, 77% is not. So 7% of the change in weight is due to just random fluctuations that are not correlated with this data. And so this kind of gives you some way of saying, oh, okay, so this is how much of the change I understand and how much of the change I don't understand. All right, so what I want you all to do is I want you to turn over to page 70 and see if you can estimate the R values, see if you can estimate the regression equation on page 70. So try to do all page 70 independently, and then come right back and watch the next video, and we'll talk about it. And that's going to be the last video before of the semester, before I send you some more exams and final exam to do. So congratulations for making it this far. You got one more very short video to look at.